Hello. In this video, we will cover section 7.4, which is on confidence intervals for proportions. In the preceding sections, we knew the population parameter p and used p to estimate sample p hat from a survey. In reality, we have the opposite. We know the sample p hat from the survey and want to use p hat to estimate the parameter p, which we don't know. It turns out that we can flip-flop the two and use the methods for estimating p hat from p, which we've done previously, to estimate p from p hat. All right, so why? The reasons that the two are linked. So switching from one to the other is just a change in perspective. If there's a 68% chance that p hat is within one standard deviation of p, which is what we did in the last section, then there's also a 68% chance that p is within one standard deviation of p hat, which is what we're going to do in this section. The way to think about it is, imagine you have two people in a room. You know that person B is 8 units away from person A. So you know that person B is 8 units away from person A. Well, you can also then say that person A is 8 units away from person B, right? So if you know that one is 8 units away from the other, then you can say, and you can go through and flip-flop it and kind of make each one as the center, depending upon your framing. All right, so when you say that person B is 8 units away from person A, you're making A the center. And then if you say that person A is 8 units away from person B, you're making B the center. And so that's exactly what we're going to do in this section. So we're going to go from having one of the two be the center and talking about how far the other is away to having the other one be the center and talking how far the other one is away. Okay, so an example can help illustrate this. Pew Research took a random sample of 446 registered Democrats in the United States in 2013. In this sample, 57% of the 446 people agreed with the statement that news media spend too much time on unimportant stories. What percent of the population, that is the percentage of all Democrats, agree with this statement? So we have the result of the survey. We have p hat. We don't have population parameter p. We would like to use p hat to try and estimate p. Our sample is unbiased, all right? So we're assuming that. So even though 57% may not be the population parameter, we expect the population parameter to be only a little higher or a little closer, right? So you expect the population parameter to be close to where your sample estimate is. You wouldn't expect it to be exact, but you expect it to be close. So how close? How much higher or lower? We can go through and use the standard error formula for that. That's the purpose of the standard error formula. So since p hat is unbiased and we expect it to be close to p, we can use p hat in place of p in the standard error formula. We go ahead and plug that in, do the calculations, and we get 2.34%. So we expect the population parameter to be within 2.34% of the sample estimate, 57%. Okay, and that's what I wrote right here. Now, so the next part is, how confident are we that is the case? So we can just say that, but is there any way that we could go through and assign some confidence or some probability to that? Okay, it turns out we can. All right, so since the sample is large, we can go through and we can use the central limit theorem to state that the sample, okay, so now we're going back to the sample is normally distributed around parameter p. This is the result from the last section. We're saying p hat is normally distributed around p. And what does that tell us? So since p hat is normally distributed around p, there is a 68% chance that p hat is going to be within one standard deviation of p. All right, so there's a 68% chance p hat is within one standard deviation of p. Now this is where the weird thing or the crazy thing or the different thing is going to happen. We're not going to flip-flop that. And so if we can say that there's a 68% chance that p hat is within one standard deviation of p, then that means that there's also a 68% chance that p is within one standard deviation of p hat. Okay, what is the consequence of that? All right, so if you put that together, what that tells us is that if we take that 57% plus or minus 2.34% from the previous page, right, the standard error stuff that we did on this page, if you go through and you take that, we can go through and we can assign a probability to that. We can go through and we can say that we expect p to be within that range 68% of the time. Okay, so again, there was some magic that happened there. We shifted the perspective. All right, so in the last section, we would have said that p hat is is within 1 standard deviation of P 68% of the time. And we're now saying that P is within 1 standard deviation of P hat 68% of the time. And this 2.34% is 1 standard deviation. That's a standard error and a standard deviation are treated the same. Okay, so what is all this? So this is called a confidence interval. The 2.34% is called the margin of error. This is how close we expect the population parameter P to be to our sample estimate P hat. The 68% is called the confidence level. This is the probability that the population parameter will be within the given interval. We could construct a 95% confidence level. So we just did a 68%. We could construct a 95% confidence level by using 2 standard deviations instead of 1. We could construct a 99.7% by using 3 standard deviations, and so on. Okay, so we can construct different types of confidence intervals based upon different levels of confidence, different confidence levels. All right, so we can interpret a confidence interval as the percentage of the time that it works, that it contains the population parameter. A 95% confidence interval should contain the population parameter approximately 95% of the time. So if we were to perform 100 surveys and create 100 different confidence intervals for those surveys, then roughly 95 of the surveys should contain the population parameter if your confidence intervals are 95% confidence intervals. Okay, hopefully that makes sense. All right, so then there's an actual simulated example on the next page. So what we're going to do is on the next page, we're going to show 100 simulated surveys where you went through and created 100 confidence intervals. And then we're going to go through and show how often those confidence intervals actually contained the population parameter. And it turns out it was 96 times out of 100, not exactly 95, but that's a sample size thing. If we went through and did 1,000 or 10,000 confidence intervals, then we would get closer and closer to 95 the more that we do. Okay, and so what you can see here is you can see confidence intervals. So the way that a confidence interval works is you do a sample estimate. I'm going to pick this guy right here. So you do a sample estimate. That's this little orange dot. And then you go through and you create an interval around it. Okay. And the idea is that that interval around it, that should contain the population parameter 95% of the time. And all of the blue/purple, all the purple dots here, those are all the confidence intervals that do contain the population parameter. And the orange ones are the ones that don't. So this confidence interval around this sample estimate did not end up containing the population. This one didn't either, nor this one, nor this one. So 4 of the 100. And that's where we got the fact that 96 of the 100 did work. Okay. So how do you create one of these confidence intervals? The first step in constructing a confidence interval is to choose your confidence level. So typical choices are either 68%, 95%, or 99.7%. Those choices align with our normal distribution areas that are within 1, 2, and 3 standard deviations. So that's not a coincidence. That there's an intent there. All right. Larger confidence levels go with larger intervals. Why? The interval needs to be larger to be more likely to contain the parameter. So if you go through and you have a confidence interval around a sample estimate, and you say there's a 68% chance that it contains the population parameter, and then you do another one that's 95%. So 95%, you're saying there's a 95% chance the population parameter is in there. You got to have a bigger interval to have a higher chance that it's going to be contained in there, to have more confidence that you've got the population parameter in your range, in the confidence intervals range. All right, so once a confidence level has been chosen, we find the corresponding number of standard deviations or standard errors. All right, so I'm going to use this throughout where I do standard deviations and standard errors. Why am I using both there? Because it's all a matter, I could use perspective for the second time. It's all a matter of perspective. All right, so in the confidence intervals we're going through and we're using results from the normal distribution. And from the normal distribution perspective, we talk in terms of standard deviations. But we're also going through and using the result of a survey. And when we do surveys, the survey distance, we use standard errors, okay? And it turns out those two things are the same. That's the result of the central limit theorem from the previous section. Okay. And so throughout the video, I go through and I put both of them because we kind of use them interchangeably. Anyway, once you've got the confidence level, you need to go through and figure out how many standard deviations or standard errors you're going to use for your confidence interval. As we've kind of already talked about, so what we got, 95%, that's about 2 standard errors. I guess this table doesn't even include 68. So 68% would go with 1, 80% goes with roughly 1.28, 90 with 1.645, 95%, that's the most common one, that goes with 2. I believe throughout this video and the homework they have you use 2. And then 99% is 2.58, and then 99.7 goes with 3. Okay. So once you've gone through and you've got the number of standard deviations, you can then go through and use that to construct what's called the margin of error. All right, so this is the distance from the center of the confidence interval to the outer edge. And so what it is it's just the product of those two. So if you say that your confidence interval, the size of it is 2 standard errors, so to go through and figure out how big that is, then you take 2 and you multiply it by the number of standard error, by the size of the standard error. That gives you 2 standard errors of size. That's the way that the margin of error works. If you're constructing a confidence interval where the confidence level is going to be 99.7%, then you want 3 standard errors of distance. And so in that case, you're going to go through and you're going to take 3 and you're going to multiply it by the standard error to get 3 standard errors of distance. All right, so that's how the margin of error works. It's in terms of the number of standard errors. Okay, and then so once you've gone through and you've gotten that, the margin of error, then the next thing that you do is you actually construct the interval itself. And to do that, you take the sample estimate that goes at the center, and then you add or subtract that margin of error, that number of standard errors, to get you the confidence interval. Okay, so you may be watching this video and you're like, whoa, man, this stuff is hitting me hard. There is a lot of theory in here. There's a lot of deep explanations, that comes from central limit theorem from the previous section. And we've got stuff from surveys from 2 sections ago. It can be quite complicated. So the goal here on this page is to simplify it. Constructing a confidence interval is just a formula. All right, that's it. That's all there is to it. It's just a formula. And this is the formula right here. P hat plus or minus Z star times standard error, where the P hat is the sample estimate. So you're going to take your sample estimate and you're going to put it here. Z star is the number of standard deviations that aligns with the confidence level. All right, so you're going to go through and you're going to figure out how many standard deviations using the confidence level, and that is from the table here. You're going to go through and you're going to start off with confidence levels, find numbers of standard deviations. You're going to put that's the Z star. You're going to put that here. Then you're going to go through and you're going to find the standard error. That's using this formula or this formula, depending upon the information you've got. If you happen to have the population parameter for some reason, you can plug that in. But most likely you're not going to have it, and you're going to just use your sample estimate in the formula. You're going to plug that in and you're going to put that here. And then you're just going to go through and just do the math, all right, to finish it up from there. So that's it. It's just a formula, and you're just going through and following steps, all right? So, but ideally, you'd go back and watch the beginning of this video and try to understand, like, why is it that we can go through and construct this confidence interval thing that says that we have a percentage confidence, a percentage probability that the population parameter is going to be within a given range. That's all the beginning part is justifying why we can do this. And it does come down to a lot of earlier theory that we've covered. All right, so now let's just jump into some examples so you can see it's just a formula. We're just going to plug stuff into the formula to calculate the confidence intervals. All right, so do a majority of teachers in the US think that digital devices are mostly helpful for students' education? In 2018, Gallup took a poll of 497 randomly selected adults who teach K through 12, and 42% of them said the devices had mostly helped. They want us to estimate the standard error and find a 95% confidence interval. And then they ask, is it plausible that as many as 50% or more teachers believe this? All right, so that's going to be an application of the confidence interval that we can do. So we'll look at that at the end. All right, so the confidence level has been selected at 95%, right? So where was that? It was right here. So you start off with the confidence level, and then we need to figure out how many standard deviations or standard errors we're going that correspond to that. So with 95%, you use 2, and that's in the earlier table. All right, so once you've got your number of standard errors, or number of standard deviations, next you calculate the standard error. That's just the formula. Plug everything in, you get the number. And then next after that, you take these two numbers, the one that goes with the confidence level, and the one from the standard error, and you just multiply them, and that gets us the margin of error. All right, that's the distance from the center of the confidence interval to the outer edge. And then to finally construct the confidence interval itself, you take the estimate value and then you add or subtract the margin of error. All right, and that's how you construct the confidence interval. That's it. All right, so step by step, go through, start off with a confidence level, use that to find the number of standard deviations, find the standard error, multiply the two, that's here, that's your margin of error, then take that result and add or subtract it from the sample estimate. All right, and the sample estimate is back here on the previous slide, 42% right there. Okay, and then from there, what you can do is you can go ahead and do the add or subtract to create a range. So if you subtract the 4%, you get 38%. If you add it, you get 46%. And so we're 95%, and the way to interpret this, we're 95% certain that the actual number of K through 12 instructors who think that devices are helpful is between 38 and 46%. So that's how to kind of tie it all together, is that once you got that interval, you can go through and interpret that interval with the confidence level as a probability, right? So there's a 95% chance that we're gonna have actually captured, that the population parameter is going to be in that 38 to 46% range. All right, and then so the question is it plausible that 50% of the teachers believe that the actual percentage is 50% or higher of teachers who believe electronic devices are helpful? If you look at the confidence interval, it does not include 50%, and since it's a 95% confidence level, that we're pretty confident that we've got the population parameter. We're pretty confident that it's between 38 and 46%. That's a 95% probability. And so it's very unlikely that the actual percentage of teachers is 50% or higher. Most likely, the actual percentage is between 30 and 80 and 46%. And so it's highly unlikely that a majority of teachers believe that digital devices are helpful. All right. Anyway, so the next one. After the Great Recession, Pew Research Center noted there seemed to be a decline in households that rented their homes and were looking to purchase homes. A couple of typos there. However, they reported that in 2016, a solid 72% of renters reported that they wished to buy their own home. Pew reports that the margin of error at the 95% confidence level is plus or minus 5.4 points. So it wants us to go through and use that information to state the confidence interval in interval form and interpret it. All right, so the confidence interval is 66.6% to 77.4%. How do you get that? That's an interval form. That is from taking the estimate, the sample estimate, and then adding and subtracting 5.4. So if you take 72 and subtract 5.4, you get the 66.6. If you take the 72 and you add 5.4, you get the 77.4%. All right, and then as far as to interpret the confidence interval, the way that you interpret it is we would say that since we're constructing a 95% confidence level, that means that we're 95% confident, or that there's a 95% probability that the true percentage of renters is in that range. Okay, example 3. So recall from a previous section that Morse believed the proportion of E's in the English language was 0.12 or 12%, and that our sample showed 118 E's out of 876 randomly chosen letters from a modern day book. They want us to find a 95% confidence interval for the proportion of E's in the book. Is the proportion of E's in the book consistent with Morse's estimate of 0.12 or 12%? All right, so again, we want to go through the steps here. First, you got the confidence level. You're told 95%. What number of standard deviations or standard errors goes with it? 2. All right, that's step 1. Step 2, we need to go through and, oh, actually, I forgot. There's another step here. One of the things with this problem is that they didn't give us the sample proportion. what they did is they gave us kind of raw numbers, the 118 and the 876. So you need to divide those to create the sample proportion first. All right, so we need to do that first. And then once we've done that, as I was starting to say, we need to go through and find the standard error. You find that just by plugging everything into the formula. And then to find the margin of error, you're going to take the product of the previous two results. So you take the product of the number of standard deviations or standard errors, and you take the standard error itself, you multiply those two, and that gets you the margin of error. So it looks like it's about 0.02307. And then last but not least, you take the margin of error and you take the sample estimate and you put them together. The sample estimate goes here, plus or minus the margin of error. And then if you go through and actually do the addition and subtraction, you're going to get a range here. It's going to go from 0.112 to 0.158. This is one way to write it with these parentheses. All right. And then the last part was, how do we feel about Morse's estimate using the confidence interval? And it looks pretty good. Why? Because the 0.12 is in that range. And so we're 95% sure, actually, that Morse is dead on. It was not dead on, but that we're 95% sure that the actual population parameter is in this range and his estimate's in that range. So that makes it pretty likely that he's correct. Okay, and now we're going to jump into some homework examples. I want to do a lot of examples of this because I wanted to make sure that people could do this. Even if you don't understand all of the details about a confidence interval, like how it works, why it works, the central limit theorem's portion of it, I still want to make sure that you can go through it. You can just calculate it because it's really not difficult to just do the calculation part. So that's why I'm including numerous examples. So according to a poll, 612 out of 1,048 randomly selected smokers believe they are discriminated against because of their smoking. What percentage of the smokers believe they are discriminated against because of their smoking? And then check the conditions to determine whether the central limit theorem can be used. And then find a 95% confidence interval for the population proportion who believe they are discriminated against. And then can this interval be used to conclude the majority of smokers believe they are discriminated against? Okay, so let's go through these one at a time. So first, what percentage of smokers believe they are discriminated against because of their smoking? To go through and calculate the percentage, you just take the two numbers that they gave in the problem and you just divide them. So it's about 58.4%. So if you talk to 1,048 and 612 say yes, then that means about 58.4% said yes. Okay, so let's just stop here for a second. So it wants us to check the conditions to determine whether the central limit theorem can be used. So the section, even the section in the textbook, the section doesn't make a big deal about going through and checking the central limit theorem before constructing a confidence interval. However, if you go all the way back to the very beginning of this video and you go through the logic behind constructing a confidence interval and the idea of that flip-flopping from one being the center to the other being the center, and that you have a normal distribution around the population parameter P, and then you can go through and shift that to being a normal distribution around the sample estimate P hat. Okay, well, one of the key things there is that idea that there is a normal distribution around population parameter P. Okay, and the only way that's true is if the central limit theorem is true. Okay, and so technically, every single time you go through and do a confidence interval, you should be checking that the central limit theorem has been satisfied so that you can go through and say that there is this normal distribution. Otherwise, you really can't go through and say that the standard deviation and the standard error are the same, that there's any link between the normal distribution and the results of a survey. All of that stuff that we're using as part of doing these problems, it's all connected to the central limit theorem. You have to have that be true in order to have that connection. And so this is the only problem in the textbook, or I think even in the homework, where it has you actually go through and check the conditions, but it's just worth mentioning that really every time you construct a confidence interval, you should be checking them because it is part of the process of creating the confidence interval is to say that the central limit theorem has been satisfied. Anyway, so we go through, we went through, and in the previous section, we checked central limit theorem stuff. And so we're just doing that check again from the last section. So random and independent, yes, that's from the word randomly given here. Large sample, go ahead and take the percent here, which is 584, multiply it by 1048. So you get 612 yeses. And then we want to do 1048 times no's, and you get 436. Both of them are bigger than 10, so our sample's pretty big enough. And then your population, to use the central limit theorem, the population has to be more than 10 times the size of the sample. And so we're going through and we're sampling 1,048 people. There are millions of smokers, so there's certainly the population is much bigger than 10 times that amount. So we're good. Central limit theorem has been satisfied, but I just want to spend a minute talking about it. Okay. Find a 95% confidence interval for the population proportion of smokers who believe they're discriminated against. How do we do that? So first, you need you use the confidence level, 95%, to find the number of standard deviations or standard errors. That's going to be 2. You use 2 with 95%. If we had a different thing, if we had 68% here, we would use 1. If we had 99.7, we would use 3. And if we had something between the two, you'd look it up in that table from earlier in the video. The standard error, we go through and just use, it's just a formula. Just plug everything into the formula. And what pops out is this 0.01523. And then to find the margin of error, you take the product of those two. So take the number of standard deviations or standard errors and the standard error itself, and you multiply them together to get the size of the standard error, really. This is the margin of error. And then you go through and the confidence interval, and then finally to find the confidence interval itself, you take the sample estimate, add or subtract the margin of error, and that gives you a range of values. Okay, and then the interpretation part is that we're 95 with a 95% confidence level. We're 95% certain that the actual population of smokers is in that range. Okay, and then finally, question D: can this interval be used to conclude the majority of smokers believe they're discriminated against? Yes. Why? The reason is because we're 95% sure that the number of smokers, the percentage of smokers, is between, 55% and 61%. Now that is above 50%. So we're 95% sure that we've got the percentage of smokers in that range, and that's above 50%. And so we're 95% sure that a majority of smokers believe they're discriminated against. And that's the way that you can look at it. All right, and what I put here is because the lowest part of the confidence interval is above 50%. Okay, another homework example. Of 1,027 adults in a certain country responding to a poll, 45% said they always or often read nutrition labels when grocery shopping. So it wants us to do a bunch of stuff. Find a 95% confidence interval, find the width of that confidence interval, name a confidence interval that would provide a wider interval, explain why this interval would be wider, construct that confidence interval, find the width of that confidence interval, and then show that the interval is actually wider. Okay, so first it says go through and find a 95% confidence interval. All right, a 95% confidence level, which it goes along with 2 standard deviations. The standard error is written there, it's calculated. Multiply the 2 to get the margin of error, then take the margin of error and add and subtract it from the sample estimate of 45%, 0.45, and that gets you a range of values. What is the width of that range? You just take the largest minus the smallest. It's 0.062. So far, so good. All right, and then question C, name a confidence level that would produce a wider interval. All right, so the way confidence intervals work is that you need to have a probability of certainty, for how wide it is. And if you want to be certain that if you have a higher confidence level, then you need to have a wider interval to have a higher likelihood that you've captured, that you've included the population parameter. Okay, so a 90% confidence interval is going to be wider than an 80%. A 95 is going to be bigger than a 95, than a 90, and so on. Okay, so hopefully that makes sense. What is an example confidence level that produces a wider interval? How about a 99% confidence interval that would produce a wider interval than a 95%? Explain why this would be wider. That's what I was just doing. The higher the confidence level, the wider the interval. And the reason is to increase the probability that you've captured or included the population parameter. Right? You need a bigger interval to have a higher likelihood of capturing it. All right, so it wants us to construct a 99% confidence interval. So to do that, first we look up, so if you look back in that table earlier in the video, where we get 2.58 standard deviations or standard errors for a 99% confidence level. The standard error is still the same, hasn't changed. We can use the previous result. Multiply the two to get the margin of error. That's right there. And then the confidence interval itself is going to be the sample estimate plus or minus that quantity that we just got for the margin of error. And then you can go ahead and do the addition and subtraction to create the range. All right, and then the width of the range is going to be the larger minus the smaller, so it's 0.08, and 0.08 is bigger than the previous result, which was 0.062, I believe. Yep. And so with higher confidence level comes wider intervals. All right, and then the last thing that we're going to include in this video is finding sample sizes from margins of error. All right, so in all the examples thus far, we have had the data from a survey and wanted to turn it into an estimate for the population parameter. We wanted to create a confidence interval where we could estimate the population parameter. What if we were the ones doing the surveying, right? What if you were assigned the task? Go and do a survey, all right? And we need to figure out, so if you were assigned that task, you need to figure out how big of a survey do you need, all right? So to calculate the size of the survey, you need two things. You need to know how big of a margin of error that you want, okay, and what your confidence level is. All right, so if you've got those two things, so, for example, I think on the next page, we're going to say that typically, the margin of error that most places use is 3%. So they want to be within 3%. They want to make a 3% guess as far as what the population parameter is going to be. All right, so if you've got the 3%, you know how close you want to be, and then you've got the confidence level, you know how confident, you want the probability is going to be. After that, it's just a matter of taking that and just plugging it into all the formulas that we've introduced in this video, and then doing some number crunching. And so, yeah, I just went through and kind of summarized this slide. A typical choice is 3% for the margin error and 95% for the confidence interval. I didn't explain why. Why are those two values chosen? They're good values in terms of getting bang for your buck. So the smaller the margin of error, which means the closer you want to actually get to the population parameter, the bigger your survey needs to be, like in terms of the number of people that you need to talk to. And so 3% gives you a reasonable balance toward a small number for your size of your error, like how far you're okay with being away from, from the sample estimate, and the number of people that you need to interview. So if you went down to like 1% margin of error, then you'd have to have a much bigger number of people that you'd interview. And if you went to 5%, 5% sounds like a big error. And so 3% is just a very reasonable sounding number. And then confidence intervals above 95% requires a whole additional standard deviation. So, so one standard deviation gets you a 68% confidence level in your interval, in the size of your confidence. Excuse me. One standard deviation gets you a 68% likelihood of capturing the population parameter in your confidence interval. 2 gets you 95%. So from 68 to 95, that's a big jump. 3 gets you from 95 to 99.7. That's a much smaller increase. And so 2 has this very middle of the road, it's big enough that 95% feels like a high number for your probability, for your confidence that your confidence interval has the population parameter. And it still comes with a reasonably small amount of standard deviations, 2 standard deviations. All right, so that's the idea, is that the two are chosen because they're like reasonably balanced. All right, so again, the goal here is you've been tasked with creating a survey and you're trying to figure out how many people do I survey? Well, once you've chosen the margin of error you're comfortable with and your confidence level, you just plug that stuff into this formula. So you've got your margin of error equals the number of standard deviations times the standard error. We've been using that throughout this section. You just plop those in there. So the margin of error, you want it to be within 3%. That's 0.03. And then the 95% confidence level goes with 2 standard deviations or standard errors. And so you get this formula. Then you take the standard error part, plop that in there, substitute that in there. And then the last piece here is, if you look at this formula, you can see that we've got two variables here, p hat and n, and n is the size of the sample. So we want n to be the only thing in this, and then we would just have algebra to solve this. So to get there, we need to come up with an estimate for p hat. And what we can do is we can estimate it at 0.5. For algebraic reasons, they're complicated. That's just that if you use 0.5 for p hat, you're going to get the biggest number for n. And it's better to have a bigger number and survey too many people than too few. That's the idea. All right, and then so finally the result when you solve for n is like magic. Boom, you get n equals 1 over 0.03 squared. It's almost too good to be true that you get that result, but it's reality. If you actually go through and solve it and do the steps, then that is the result. And then if you recall that where did this 0.03 in the formula come from, that was the margin of error. And so if we wanted to do different margin of errors, we could think about putting different values. So instead of putting 3%, if we wanted a 5%, we would just get 5% here. And so it turns out we can simplify this formula and make it a little more generic by saying that the size of the sample needs to be n equals 1 over the margin of error squared. That is like such a very nice formula. It's a miracle it comes out that way. All right, let's do an example. So a recent study asked the question, what percentage of children in California between the ages of 2 and 11 drink at least one sugary drink per day? We want to calculate a 95% confidence interval for this estimate, and we want the margin of error to be 3 percentage points. So plug 0.03 into the sample size formula on the previous page and solve. And if you do that, you get 1,111. So that tells us the survey needs to have at least 1,111, and it's that simple. Once you've got the formula, you know, it's really easy to just pop stuff into it and get the result. Okay, let's finish up with one more homework example. So consider a study conducted in 2018 where researchers wanted to estimate the percentage of middle school girls who plan to major in a STEM field. If a 95% confidence level is used, how many people should be included in the survey if the researchers want to have a 17% margin of error? And how could the researchers adjust their margin of error if they want to decrease the number of study participants? All right, so first, if a 95% confidence level is used, all right, then we can go through and pop that into we can pop the 70% margin of error into our formula. All right, so if you go ahead and put that in here, we end up getting 35, and that's all there is to it. You just take the margin of error, plug it in. Now, this only works for a 95% confidence level. If we have a different confidence level, then you would not be able to use this formula. All right, and so once we've done that, we can say that 35 people need to be in the study to have a 17% margin of error. How could the researchers adjust their margin of error if they want to decrease the number of study participants? So if they say 35 is too many, all right, so if 35 is too many, then what you'd need to do is you'd need to increase the margin of error. So the two values, the margin of error and the sample size, are said to be inversely proportional. That's what this type of formula means. So if you've got 1 equals 1 over the other, that means that as one increases, the other decreases. So if the margin of error goes up, then the sample size has to go down. If the margin of error goes down, then the sample size has to go up. All right, and so if we're going to have if we want to have fewer participants, then that's going to mean a bigger margin of error. Okay, thank you for watching. That's the video. I'll see you next time.